Okay, so reproducible research for OMNeT++ based on the Python and Pweave. Actually, I'm greatly indebted to the Andras about the preparation of today's tutorial. Originally, I was preparing this tutorial based on R, the choice of the statistical programming language, and then Pweave. How many of you actually heard or used R before? Okay, significant number of them, that's good. But right now, the R community very quickly moving to Python for obvious reasons, because if you use the R extensively for large-scale simulation, I will show later some of the code snippet, but it's not very, how can I say, easy language to work with. It's very specialized languages for statistical programming, but anything longer than maybe several pages is not very comfortable to program with. Okay, very short the size program. R is definitely good. Still, R is the best language in terms of the code base for wide variety of the statistical technique. But for example, in our case of the engineering domain, especially simulation domain, Python is more than enough. So I'll talk about it because right now the Python is really, really popular. And even I'm just working a little bit on the artificial intelligence and machine learning. You know that, for example, right now everyone is talking about machine learning, deep learning, especially last year, this year, AlphaGo, the machine learning, deep learning neural network beat the human champion. Of course, some people, maybe especially the Western side, what's the deal? Because maybe several years ago, Deep Blue already defeated Kasparov, am I right, at the chess? But to tell the truth, the complexity of the chess and the Go cannot be comparable with each other. All possible cases of the game Go is more than the whole number of molecules in the universe. So until last year, many experts in the field is maybe in the foreseeable future, artificial intelligence definitely never ever can beat the human champion. But that happened last year, and this year again, the youngest international champion. So right now, the shock and impression in Asian side is completely different, because not many Western peoples know the Go very well. Am I right? So, so even though this is a tutorial, but I have to admit that this is a very not a well-made tutorial. But I'm just to give you some taste of what is a working document. For example, in a previous presentation, Anna mentioned that Anna and her students contact the original author of the paper, but they even forget about it. Am I right? All the details about it. So today's tutorial is exactly the aiming for that kind of situation. But not just, for example, another author. I myself found myself in a similar situation, because I finished a certain simulation work a long time ago, but several years after, I visited my own work in the past, but I forgot all the details about it. So quite hard time to revive what I have done, or what's the problem, and what kind of configuration. So reproducible research is really the hot item right now, hot issue. So simply speaking, reproducible research is a key to any scientific method and ensures repeating an experimental results of its analysis in any place with any person. This is very important. Sometimes you are sure that, oh, I definitely produced the fantastic results, okay, and then published a good paper, but readers of that paper tried to repeat the same experiment but couldn't get same results, okay? That's very frequent, even with OMNeT++. I received several questions for my past work. Hey, Joseph, I read your paper. I've tried to repeat the results with my own simulation. Couldn't do that. There's various reasons, definitely. Of course, the version difference and maybe certain configuration issues. So there's many subtle details which usually not kept in the traditional publication. So this reproducible research among research community, the people find out that that's a serious problem. I will show you quickly after these slides. There's some good and bad example of reproducible research. So how can we make our research work complete, especially current traditional printed publication cannot capture all the details of the experimental work. So some people actually intentionally used it he or she knew that there is some weakness in his her work, okay, but didn't explicitly mention the publication. Roughly saying, oh, we did some simulation with blah blah model without providing all the details about it, then actually readers cannot have no idea, no clue. He or she tried to repeat getting same simulation results many times, but couldn't get it, okay? So a study can be truly reproducible when it satisfies at least the following 3 criteria, just minimum criteria. All experimental methods are fully reported. In our case, all the OMNeT++ input, like a NAD file, INI file, or version number, or whatever, should be recorded and published. All data and files used for the analysis are publicly available. I think Andreas is preparing very nice web-based, IPython notebook-based tutorials in this regard. So I don't want to go details in this area. I think Andreas will announce very soon availability of the new OMNeT++ tutorial based on Python iNotebook web interface. The process of analyzing raw data is well reported and preserved. Again, this is related with the second item. So once all the scripts, okay, and all the methods, analysis techniques available in one document or one web page, then all those hassles or difficulties can go out. Am I right? So reproducible research is basically to ensure you have same data, same analysis script. In principle, you should get same results whenever, wherever, whoever. Okay? So idea is that simple, but to implement this idea is not that simple. Quite a lot of challenging issues. I'm not sure if I have enough time, but I definitely need to want to share with some examples. Why do we need reproducible research? 2 examples. First one is a LIGO, gravitational wave detection. If you are interested in the physics area, last year, some of you can remember that there's huge highlights in the newspapers, broadcasting, because after more than 100 years, Einstein's the relativity theory, you know what? The Einstein predicted by theory that there will be gravitational waves, am I right? Sudden change of the mass in the stars or universe, whatever, then that causing some generation of the gravitational wave. So theory already predicted a long time ago, more than 100 years ago, but last year, this LIGO, Laser Interferometer Gravitational Wave Observatory, the huge linear devices, I think several kilometers long, finally detect the evidence of the, where is laser pointer? Okay. Where's the laser pointer? This one, okay, thank you. Okay, great. It's reported in the last year, February 2016. And that report is actually published in series of papers, but the first one is published in the Physical Review Letters. Nature Science also covers it. But the important and the relevant for today's talk is this IPython notebook, the one I mentioned that Andreas is preparing the tutorial for. So if you go to the link, you can actually download, and then you can run and then test the experiment with yourselves with actual data used for this Physical Review Letter paper. Okay? So this is one good example of reproducible research, and actually increasing number of publications, they provide this IPython, which is right now the name change, Jupyter notebook with all the data and analysis script. Okay? This is one good example of reproducible research, nearly Nobel Prize winning level of the research. But unfortunately, one of the, I think, the first author, I think, died very recently. So he was the screen effect creator of the Hollywood movie Interstellar. I'm not sure how many of you have watched the movie Interstellar. There's a very notable scene representing black hole. The hero actually falling into the black hole. Then there's a fantastic scene which is generated by computer graphic. But that is based on rigorous physical theory, okay? And one of the first authors of this research was behind that scene, and then also he was the key in this research, but I believe that he passed away late year or early this year. So unfortunately, he couldn't enjoy the Nobel Prize. This one is maybe relevant to the German in this audience, I'm sorry. Kyeong, even though I may pass on some time, but I have to mention this one, especially the young researchers in the audience. I think this is a very important message for you. Actually, he and I worked in the same period of time in the Bell Laboratories headquarters, Murray Hill, New Jersey, around the 1997 and 8. Of course, his quality is beyond the imagination. I'm just a normal researcher, but he was a rising star, okay? After several years of the fantastic work, he was supposed to be head of Max Planck Institute in Germany, okay, one of the biggest and the best physics research institutions. He was much younger than me, but at the time of both of us working at the Bell Laboratories, he was already highlighted, covered by many Nature, Science, journals and broadcasting, blah, blah. In his high time, he published papers in every 7 or 8 days. That paper is not just like, I'm not underestimating the importance of our community summit, not like a conference or workshop paper, but every paper is like a physical review letter, Nature and Science papers, in average 8 days, okay? So around the 2 or 3 years he's working at the Bell Laboratories, I believe that he published more than 80, nearly 90 groundbreaking papers. Every paper is groundbreaking papers. And because of this one guy, molecular computing, this really died actually. So maybe most of you never heard about it, okay? But at that time, molecular computing is much like a current days artificial intelligence, deep learning, or neural network at that time. Several hundreds of the most brilliant physicists, PhD candidates dedicate themselves for this molecular computing, but later they found them doomed. Actually, this new area of the molecular computing is based on the first research. What happened is that some people found out that several of his papers, actually, the graphical plot is exactly identical for different experiments, but actual plots are identical, but not exactly identical, slightly changed in the direction or scale, blah, blah. But some cautious readers find out that actually the 2 different papers, they sampled the plots, and after scaling and then zooming in, zooming out, they found that these exactly overlapped each other. That's the beginning of this frauding story. So by the time when I moved from Bell Labs to Stanford Networking Research Center 2001, this fraud case was already highlighted in the news. Then the world's top physicists formed the investigation, the committee, and interviewed he and many of his co-authors. You know what? During the investigation, he mentioned that, hey, where is your lab notebook? Where is your experimental data, experimental samples? He mentioned, oh, because of the lack of space, I removed all the data in my hard disk drive. Hard disk drive is actually fallen, out of order, and he never kept the laboratory notebook. So basically, there's no evidence, no records, no data, even after publishing nearly 90 groundbreaking papers. Can you imagine? All he says is that I clearly observed them in the lab. I built a molecular computer in a molecular level. I observed that, but blah, blah, blah region, I have to remove all those data because of the lack of the space in the hard disk. Can you imagine that? So actually he fired, and then his PhD degree is actually withdrawn from his alma mater. And nobody knows for sure what he's doing right now. I think in the Wikipedia, I recently checked that he's working with some engineering firm, but anyhow, he's virtually kicked out of the scientific community. Of course, this is one extreme example of the bad case of the reproducible research. Many people try to reproduce his research reported in nearly 90 papers, but no one can reproduce his research results. Then after several years of such a failed story and an investigation, and he finally kicked and fired and completely kicked out of the research community, okay? So yes, that's good. We just so far focusing and will focus on the how good this protocol and how innovative these technology schemes, whatever. But at the same time, we need to think about this reproducible research. Not only for readers, but for yourselves. Maybe after several years, unless you have very good memory, chances are even you have hard time to understand your own simulation code and configuration files. Actually, at least that's the case for me. Okay. So, tool of choice for this reproducible research for OMNeT Plus is Python and Pweave. And traditionally, R and Pweave was the choice of the tool for this job. But as I said before, R is really good for very short work, but the very long programming, much like MATLAB. MATLAB is not, how can I say, full-fledged programming language. It's good for testing and prototyping. But whenever you want to implement something serious, you may hear lots of the complaints, especially computer scientists extremely hate MATLAB. Okay? So that's why most of the leading universities, especially in the United States, already moved to the Python. Already, I think, 10 years ago, starting with the MIT. They changed their first fresh level computer programming course from Scheme. You know this, how many of you know the Scheme? Is Lisp. Dialect of Lisp, then to the Python. Then after that, many of the universities is moved to Python. So the R Suite 2 and Python Pweave, and like IPython and now Jupyter, they changed the name. R provides then called the Sweep, and because of the time, I'll just maybe better to with the actual examples. Actually, this is called a snippet of the R source code. And as you can see here, they are not using the equal sign for the assignment. Just very peculiar arrows, the shaped the operator for assign or blah blah. So maybe several years ago, I had to use R extensively, but I was not very happy, definitely. And this is R code, and this is a Pweave code. You see that this is a familiar LaTeX command, am I right? In the middle of LaTeX code, we use this double bracket and the alpha sign. In between, we can insert or introduce R code. Then later, with some special processing, we can integrate the results of this R in the middle of the LaTeX. Okay? So this is an overview of the general procedure. How can we integrate the code and the code results into in the middle of the code, documentation. So right now, today we are using Pweave. As you can see, the P stands for Python, and the Weave is, you know, that the terminologies are making into fabric from strands. And the mix of documentation code chunks in one file, typical extension is PLW. To generate the documentation, we just simply weaving. Then document and original code chunk, this part is actually replaced by the results of this code. Okay? So documentation, results of the code, documentation, result of code, all just integrate into one final source file for text or markdown, restructured, or various kind of format is possible. Sometimes maybe there are lots of the code chunks, and then you need to definitely debug it. Then you can tangling. Tangling means out of the same PLW file, you can extract code chunks and then end up with one Python source code. So you can just run and debug it as usual with the typical Python source code. This is really good for debugging purpose. And this is Weave example. By the way, don't worry about it. I already prepared the GitHub repository. So all the materials and the sample PLW file and even these slides is available in that GitHub repository. Compared to IPython or Jupyter Notebook, which actually Andres is preparing for, one notable difference between IPython Notebook and this Pweave-based documentation is, in my opinion, is table. IPython Notebook, as far as I know, there's no way of generating good long table, am I right? Just mostly the plotting and the graphic. But the Pweave, compared to IPython or Jupyter Notebook, you see this same PLW source code, okay? Here is just normal text, Then after that, as I said, for double bracket and alpha, we have the very short 3 lines of the Python code. Then after weaving and latexing, we can get automatic table, and that table actually, depending on the size of the data frame, why I cannot, this is a slide. Oh, maybe I have to finish the slides. And go to the, I want to go to the PDF, this one. Still a slideshow, am I right? Maybe it's end the slideshow? Oh, okay. Okay, great. Sorry about it. So in the previous slides, I just only show this part, but actually that 3 line of the code can generate all the data inside your data frame automatically. Okay? So can you imagine that preparing the same table manual way? Of course, it's not for publication, but this is for snapshot of the your research, your own internal record, okay? So just this 3 line of code, then we have all the data inside the data frame in this nice long table format. Yes?
Analogous to the df dot to LaTeX, there's also to HTML, so it should work with IPython.
Oh, that's a good point. I didn't know that there's some HTML file, yes. But in such a case, in IPython, you know that cell is, how can I say, there's a different cell for command, different cell for markdown, Python. So that command is part of the code, am I right? So after executing that code, that definitely generates the HTML code. But in one cell, some part Python, some part HTML is possible. Maybe these technical details, okay? Yeah. So this is one notable example. Yeah, F5, yes. No. Yes, great. So this is a general discipline. Then this is a specialization for OMNeT++. So how to deal with the simulation input files? The starting point, okay? So if you deal with the very small simulations, we can include the simulation configuration files like INI, net file directly inside the document, much like this, okay? But if your simulations consist of the tens of sometimes hundreds of the simulation configuration files, I cannot think of any good solution other than maybe providing git commit rather than just including directly those configuration files inside of your document, but you can maybe use some git commit hash, okay, as an indicator for the several hundreds of the simulation configuration files. But this is only when your simulation and everything is controlled under some version control system. So this is something you have to think about it. I do not have a perfect solution. How to guarantee match between input files and output data? Even though I provide the input files in my one documentation, and also at the end of that documentation, I provide the data and the table and plot. But how can you guarantee this data, these plots actually generate from previous simulation configuration? How can you? Just in the middle of the preparation of your paper, okay, still you just analysis and then graph is based on the previous simulation data, but in the middle of the working, oh, looks like I need to change that parameter and then run the simulation again. Then chances are your simulation data, plot analysis results, and your up-to-date simulation configuration files maybe not exactly match each other, am I right? Again, very small simulation, we can include everything. I will show you in my sample file. This sample documentation, whenever you change the simulation info configuration, it can automatically detect the mismatch between the two, and on the online, they just rerun the simulation. This is possible for very short and small simulation. But how about the most of the presentation today? I'm pretty sure it runs maybe several hours or sometimes several days. It's definitely not a solution. Yeah, again, as I said before, the only thing I can think about is maybe Git commit hashes as an indicator of the kind of a complete snapshot of input, source code, even possibly simulation output data. Actually, I tried this approach, but the problem is that GitHub free account, there's a size limit for a repository, okay? But simulation data sometimes several tens or hundreds of megabytes. So this is, again, is maybe not a practical solution. So I'm just suggesting this is a challenging point, and I don't think about any perfect solution yet, okay? And the how to present and analyze output data, this part, maybe I'll skip it, because Andres preparing the IPython notebook tutorial is much, much better in regarding how to analyze and how to use pandas and generating plots or whatever, because I already nearly passing the time. So I'm just skipping this actual part. And just maybe a couple of minutes of the final demonstration. So nearly done with the slides. So actually, I prepared one small sample file. This is a result of this Pweave file. Very small, but this is a complete instance of all the necessary features, okay? There is a small, can you clearly hear? The batch file, just 2 lines. First one is Pweave, as I mentioned in the overview diagram. So they're first processing the PLW file into LaTeX. The resulting LaTeX is processed by the LaTeX, and then producing the final PDF. That's the result is this one, okay? Then I'm just showing the one. Because this is a very small one, it's taking just less than 30 seconds or something like that. So first there's the weaving. So weaving is executing those Python code, and then integrating the final results back into the LaTeX, and then the LaTeX part. It's very simple and short, and we have the same, this one. But I'm just, again, as I said before, maybe I was something wrong, that maybe simulation is too long, so let's make it short for the purpose of this demonstration, just 5 hours. Then maybe just 3 different cases. So I just slightly changed my initial the simulation configuration, am I right? So in such a case, if we run this Pweave again, you see they're actually running simulation again, because they detect a mismatch between simulation configuration file and actual timestamp of the previous simulation results. This simulation configuration file is newer than the simulation results. So as I said before, the simulation is very small and quick, and this could be a solution. It's much like IPython notebook. IPython, JPython notebook is have everything inside one note page, one web page, okay? So every simulation execution code, whatever, can be within one notebook web page. So you see, previously there's a, what's the problem? The problem is that the resulting SCA file is still remaining there. So that's why, sorry about it. Even though we run simulation again, but there's a loss of the SCA file from previous case. So let's see that how it automatically updated in the meanwhile. So there's total 5 points.
That is because you included iteration variables in the file name.
Iteration variable. It doesn't matter, because that is a scave tool. The process all the files in the same directory. So you see that right now. So from 5 to reduce to 3, okay? So they detect some changes in the final one, not just the computation file. So I'm not happy with this blue color, so let me change it into red color. This is nothing to do with simulation, but just presentation analysis. In such a case, running the PW again, not running the OMNeT Plus simulation at all. They automatically checking something, so they only just going through, so no simulation, am I right? Just latex. So sometimes I changed my simulation configuration file, sometimes I changed the analysis and the presentation part, okay? But once you have the good PLW documentation file, they can automatically checking whether we need to run OMNeT simulation file or not, okay? So this is very small sample file and then small tutorial, but hope that you can have some idea why having every necessary information in one file is important. It is final comment, because why I use the R extensively, because 3 or 4 years ago, my research requires total more than 4,000 simulation runs over a month with a very large Linux cluster computer, more than 200 cores. So that's why I spent a lot of time to this automation and this reproducible research at the time. And this is another snippet of, at that time, this is created by the R and the Pweave, not the Python and Pweave, okay? There are lots of long table, just kept for internal purpose, okay? So that's it. I'm sorry to spend too much time, but maybe we can discuss any questions or whatever, because we are already passing 10 minutes. Thank you so much. It's a coffee break. Thank you.